A wandering asteroid is found, and we need to know the acceleration of gravity to begin with, only given the radius and the density. Yeah, so it's possible to work out the mass, I suppose, and do it that way, but this might be useful later. I know little g is big G times m over r squared. That's actually 4/3. It's big G times 4/3 times pi. That's the volume, 4/3 pi r cubed times the density divided by r squared. And that cancels to give me 4/3 big G pi r rho. So if I plug that in, that will give me 6.67 times 10 to the minus 11 times pi times 500 times 10 to the 3 times the density. That gives me 1.12 meters per second squared as the gravity. And then it tells us that a careless space engineer, falls down the hole, and he falls through the asteroid. I suppose he comes out of the other side, and then he starts falling again, back again. So we've got an asteroid here. I suppose it's got a little tube down the center, and the poor engineer falls down and then comes back up again because the gravity will pull him back in the other direction, a bit like a mass on a spring. It says to use the equation A equals minus omega squared x. And if we look at what we got earlier, it's the same thing. G equals 4/3 G pi rho times r. And that's my acceleration there. And that's my displacement there, because as he falls, he is effectively on the surface of a smaller and smaller planet with that radius identical to his displacement from the center. Therefore, the angular velocity is equal to 4/3 G pi rho, which is also equivalent to the gravity divided by the radius. But anyway, time period is 2 pi over omega. Let's get omega first. So I'm just going to work that out. 4 divided by 3 times big G times pi times the density. Square rooted gives me an omega of 1.50 times 10 to the minus 3. If I put that back in there and do 2 pi divided by that answer, that gives me a period of 4,200 seconds. And to get it into minutes, I get a time of 70 minutes, which only depends on the density of the